Hey everyone, and welcome back to the channel. Today, we're diving into the fascinating world of derivatives, a cornerstone of calculus that unlocks so much understanding about our world. In this video, we're going to tackle 4 fundamental rules that will form the bedrock of your derivative-taking skills: the constant multiple rule, the sum rule, the product rule, and the mighty power rule. By the end of this, you'll be able to differentiate a wide range of functions with confidence. Let's get started. Alright, first up, let's talk about the constant multiple rule. This one is super straightforward. Let's consider 2 water bottles that start empty, then get filled at different rates. At any given time, one bottle has twice the amount of water as the other. Let's call W1T the amount of water in bottle 1 at time t, and W2T the amount of water in bottle 2. At each instant of time, the volume of water in bottle 2 is twice that of in bottle 1. So, these 2 functions are related as W2T equals to 2 times W1T. Now, as you can see, both the functions are linearly dependent on time, and if measure the slope of each function, we get same relation between them, that is, W2 prime equals to 2 times W1 prime. So, we can conclude that the derivative of 2W1T is equals to 2 times W1 prime t. A multiplied constant, like 2, can be moved in and out of a derivative. This property holds true for any multiplied constant. Next, we'll explore what happens when we add functions. To understand the derivative of a sum, let's consider a water capture system with 2 sources. The sources, V1T and V2T, have flow rates of V1 prime and V2 prime into a large container respectively. At time t, the container holds V1 plus V2 liters of water. Now, if someone asked, how fast is the container filling at any given time t? The answer should be the combined rate of both the sources. So, if the total amount of water in the container at time t is V1 plus V2, then the rate of change of that amount would be V1 prime plus V2 prime. We can also prove the sum rule using the limit definition of the derivative. Consider 2 functions, f of x and g of x. By applying the limit definition to the sum of function, we get the same result. More generally, we can say the derivative of a sum is the sum of the derivatives. We can say this formally as the sum rule. Next in the list is the product rule. To explore the derivatives of products, let's start with the area of a square. When we stretch the square so that its side length increases from x to x plus delta x, its new area would be equal to x squared plus 2x delta x plus delta x squared. The increase in area, delta A, would be equal to 2x delta x plus delta x squared. For very small variation, the change in area would be approximately 2x delta x, or in derivative form, del A over dx equals 2x. Let's take a similar approach with the derivative d over dx of fx gx, where f and g are both smooth functions. We'll compare the original rectangle with a stretched rectangle. Here, delta f equals f of x plus delta x minus f of x, and similarly delta g equals g of x plus delta x minus g of x. If delta x is small enough, we can ignore the piece in the lower right corner, just as before. So, the best estimate for the change in area would be fx delta g plus gx delta f. As delta x approaches 0, the change in area, d over dx of fxgx, would be equal to fxg prime x plus gxf prime x. Next, we'll find a rule for derivatives of functions with powers. Before we make the leap to find a general power rule, let's use the product rule on function x cubed. To do so, we will write x cubed as x times x squared. Since we already know the value of derivative of x and x squared from our previous example, by using them and applying product rule, we get derivative of x cubed equals to 3x squared. If we use the same process on x to the power 4 by splitting it into two functions, x and x cubed, we get its derivative equal to 4x cubed. Now, if we look at the derivatives of these functions, we see a pattern is emerging from them. And if write it in more generalized form, we can say the derivative of x raised to the power n is equals to n times x to the power n minus 1. Although we only use the positive integer values of n for so long, but the following expression is also true for any real value n. And there you have it. We've covered the constant multiple rule, the sum rule, the product rule, and the power rule. These are your foundational tools for differentiation. In our next video, things get even more exciting. We'll be tackling the chain rule, the quotient rule, and then using all of these rules to solve real-world optimization problems. Thanks for watching, and I'll see you in the next one.